Hey there, it's Shannon MATHCHICK Myers, and we are on part 2 of section 10.1 from the Larson and Edwards early transcendental text. We are checking out ellipses and a little bit of calculus. So an ellipse is the set of all points x and y, the sum of whose distances from two distinct fixed points called foci is constant. So if you have, let's just make a little quick visual. It's hard to be perfectly center. So if this is the center, HK, so I might as well do this one as well. Looks pretty good. And we have two foci. So say we have one here and one here. It's fairly elongated, so it might even be a little further. The more elongated the ellipse, the further away from the center the foci are. Check. Check. And let's say you've got some point x1, y1, and another point x2, y2 on the ellipse. And basically what's happening is you've got this distance here, from x1, y1. This is the distance between the foci, right? Connectors. And then from x2, y2, you've got this one and that one. And so you end up with these different distances. We'll call this distance 1 and distance 2, distance 3 and distance 4. I'll highlight them because otherwise it's hard to see. So distance 4 is this one. Distance 3 is here. Distance 2 is this guy. And distance 1 is here. So it turns out it's pretty cool, actually. Like, if you connect a string, right, to a pencil and pin the string in where the foci are, you basically can draw out your ellipse. So it's kind of very cool to do that. So let's just take a look at some of the other interesting stuff. We have, for ellipses, have a minor axis and a major axis. So the minor axis, in the one that I've drawn here, the minor axis is the smaller value. I don't think I was quite center. And then the major axis is your larger, so the longer one. this one would be the major axis. This would be our minor axis. And they don't have to, you know, they could be anywhere on the plane. All right, so now the placement of the vertices are way out on the edge, so that would maybe be vertex 1 and vertex 2. They're in line with your center, as well as the foci are in line with the center. We did something like this, where this is focus 1 and this is focus 2. Cool, cool? Now, the length B, all right, is this distance here, the distance between the minor axis and the vertex. And then the distance A goes, I'm going to draw it a little differently, from like here to here. So this would be A. This would be A. And then C is this distance right here. Cool, cool? All right, so here we go. The standard equation of an ellipse, of this theorem, the standard form of the equation of an ellipse with center HK and major and minor axes of lengths A and B, where C squared equals A squared minus where A is greater than B. That's how you tell the orientation of your ellipse. So what you'll have is, if your major axis is horizontal, it'll look like the picture we were working with there. So you'll have x minus h squared over a squared plus y minus k quantity squared over b squared equals 1. And then the major axis being vertical would be, you can write it the same way. The h always goes with the x, the k always goes with the y, but this time b squared will be under the x. And a squared will be under the y minus k quantity squared. The foci lie on the major axis, C units from the center, and remember that we have C squared is A squared minus B squared. And then, so you have your, when your major axis is vertical, your foci will be at, or sorry, when your major axis is horizontal, your foci will be at h minus c, comma, k, and h plus c, comma, k. When your major axis is vertical, it'll be a shift in the up and down. So you'll have your foci at h, comma, k minus c, and the other one will be at h, comma, k plus c. And then your vertices will be A away from the vertex. So when the major axis is horizontal, again, it's a shift on the h. So you'll have h minus a, comma, k, and then h plus a, comma, k. When the major axis is vertical, it'll be a shift up and down. So your vertices will be at h comma k minus a and h comma k plus a. Groovy? All right, so here we go. There's a reflective property of an ellipse, which is interesting. If we let P be a point on an ellipse, the tangent line to the ellipse at point P makes equal angles with the lines through P and the foci. So you've got your foci here. That's your focus 2 and focus 1. And you've got this line here going through P. They have it extended through Q. And then you've got this other line here, the other focus here, right? And it turns out that extending this line out to Q basically gives you the same distance or the same length of segment from PQ to PF1. And so that ends up giving us equal angles across that tangent. So that's a very cool property of an ellipse. Now, as eccentricity of an ellipse is denoted by E, and it's given by the ratio E equals C over A. For an ellipse that is close to being a circle, the foci are close to the center, and the ratio C over A is close to 0. An elongated, like a stretched out ellipse, has foci which are close to the vertices, and the ratio C over A is close to 1. Cool, cool? All right. So let's check out how it works. Again, there's always that potential for completing the square. Fun times, right? So let's crunch through. We need to find the foci, vertices, and eccentricity of the ellipse and sketch its graph. So here we go. Let's work with this equation. We have 16x squared minus 64x plus 25y squared plus 150y equals negative 279. Now I need to factor out 16 from the x terms. So inside I'll get x squared minus 4x. To complete the square on this one, I'm going to have to add negative 2 squared inside these parentheses, but I've really adjusted that parenthesis by how much? Good. 4 times 16, which is 64. So I'm going to put an equal sign a little further over, and then I'm going to add the 64. Now we've got to factor out 25 from the y term, so we'll have y squared plus 6y. We will be adding 3 squared, which is 9 inside the parentheses, but 9 times 25 is what we've really adjusted the equation by since we factored out the 25. So let's see, 8 25s is 200, so 9 25s would be 225. So then we'll have 16 times x minus 2, the quantity squared, plus 25 times y plus 3, the quantity squared. And when we combine the constants, we end up with 10. Now we want to get 1 for on the right side of the equation. So I'm dividing everything by 10. When I divide 16 by 10, I will get 8. Sorry, I will get, not 8. I will get, yes, 8. 8 fifths times x minus 2 quantity squared. And then when 25 divided by 10 is 5 halves when you reduce. And that's times y plus 3, the quantity squared, will now equal to 1. Now, if I want to find my a, I kind of mess it up a little. So I'll have x minus 2 squared divided by 5/8. So do you see how if you invert and multiplied, you'd have your 8 fifths you started with? Awesome. So similarly, we'll have y plus 3 quantity squared divided by 2 fifths. And that's all equal to 1. How are we doing? All right, awesome. So now let's go ahead and just take a look at what we have so far. So we know that a squared is 5/8, and a is the square root of 5/8, which is approximately 0.79. B squared is 2 fifths. So B will be the square root of 2 fifths. These are positives, so we're not worrying about applying a plus or minus. And then finding an approximation, just so we can graph it, will be it'll be about 0.63. So this is going to be, you know, the A and the B are not too far apart. So this is going to look very circular, kind of very circular here, but not quite a circle. Now we know that c squared is a squared minus b squared. So c squared is, we know a squared is 5/8, b squared is 2 fifths. And so c squared, if I get a common denominator, will be 25 minus 16, which is 9, all over 40. And so c is approximately the square root of 9/40, or exactly, sorry, which approximates to be 0.47. Cool so far? All right, perfect. So since we do want to graph these, I think that we will definitely round our foci and our vertices. So let's do it. Our foci, so focus 1 will be, do you see that 5/8 is greater than 2 fifths? And so our A is underneath the x minus 2 quantity squared, which means we have our major axis is horizontal. So the shifts will be on that horizontal axis. So we'll have H minus C comma K, which will be approximately, H is, we didn't do our center yet. So what is our center? So H is going to be, do you see that here's our H, and then K will be -3. You'll have to flip the sign. So let's graph that. We'll write that in. Center HK equals 2, -3. All right, so 2 and then 1, 2, 3 down gets us our center. And then our first focus will be H, which was 2, minus C, which is 0.47. So we'll have it at about 1.53. And then K is -3. And then our second focus will be H plus C comma K, which is approximately H, which is 2, plus 0.47. So 2.47, comma, -3. Good so far? Excellent. So let's graph those. I'm going to come in really close, so because it's the scale is not fabulous for this. And so we have we'll be down at -3. We have 1.53, which is about here. So 1.53 is roughly there. And then 2.47 is roughly here. And then for the vertices, we'll come back to the drawing board here. So our first vertex will be at H plus A comma K, which is, H is 2, and A, that'll also be approximate. We got 0.79, so we'll call it 2.8 comma -3. And then our second vertex, H minus A comma K, will be 1.21 -3. And again, coming in close, we'll have it about here and about here. So very close. Now, just to get the feel for how to draw this one, we're going to look at B, and we're just going to go from HK. B was 0.63. So I'm going to go 0.63 up, 0.63 down, and then our ellipse will be that little teeny tiny graph. Sorry, it's so little. Cool, cool. All right, excellent. Now we are tasked with finding an equation of the ellipse with vertices 0, 3 and 8, 3, and eccentricity E equals 3/4. So what do we know? We know that the shift is on the x's or the y's? Beautiful, the x's. And so we've been given information. The eccentricity deals with C and A, right? So we have vertices. So we have H minus A will equal to 0, and H plus A equals 8. So when I add those two together, I'll get 2H, the A is 0 out, will equal to 8. And so H is 4. Now back substituting, I'll do the H minus A is 0. We have 4, plugging in for H, minus A is 0. And it looks like we'll get 4 is A. So A and H are 4. All right. Now, what else do we know? We know that our eccentricity is 3/4. And we also know in general it's equal to C over A, that ratio. So using this information, we can go ahead and say that 3/4, which is the eccentricity, is equal to C over what we found for A, which was 4, right? And so therefore, C has to be 3. And now we can find B. So C squared equals A squared minus B squared. We found that C was 3 and A was 4. So plugging those in, we'll have 9 is 16 minus B squared. With a little algebra, we get B squared is 7. And that's all we need. We don't need to square root it because we just need to write the equation of the ellipse. So our center is HK. We said that H was 4, and we know K is 3 from the given order pairs. So X minus 4, the quantity squared, over A squared, that'll be 16, plus Y minus 3, the quantity squared, over B squared, which we found to be 7, is equal to 1. And we found everything. Groovy? All right, so if you missed the part about that deals with parabolas, check out part 1 of this series for 10.1, and we'll be going on to hyperbolas for the next part. I hope you have a wonderful morning, afternoon, or evening, whenever you're watching this show. And hey, if you like what I'm doing, go ahead and click on that like button, subscribe, maybe share the video, and I'll see you later. Bye.